Hello my dear friends, we have already knocked out continuity, so today we are going to knock out differentiability. Welcome back my dear friends. As I rightfully said, we have knocked out continuity and today we are going to knock out differentiability. Alright, so welcome back once again. I hope all of you are doing very well. Time to get back to business. So as I was telling you, we are going to start with differentiability. That's the second topic from calculus, from differentiation, from chapter 5. So it's a very small topic as per our textbook. It's not very small, but yeah, as per the textbook, it's very it's a small topic. We have like two questions. We have two questions from the exercise plus some examples, but definitely I'll also be giving you some other questions also, one or two, not many, don't worry. So we are not going to waste too much time on this topic, differentiability. I'm going to give you exactly what do you mean by differentiability in very brief, in concepts and details and all. Yeah, we can discuss about that later on also in some other videos. And of course, you can just check out the concept of differentiation also. So it's very much related to all of that. So as I said, in brief, I'm just going to give you, it's not good to just jump, even though it's a very small topic, it's not good to just jump because small things can give you the most biggest headache. No? So we will at least learn and try to understand what is exactly differentiability at a point, in an interval. We will know the concept of differentiability at a point today. Okay, differentiability at a point. We will be talking about that. I'll limit myself to the textbook only. Alright, so alright then, this is the first thing that we need to know before we really go to differentiability at a point. So this is the first thing that we need to know. As I said, the other topics about differentiability and all, yeah, we can discuss that later on as we proceed. But for now, today we are going to limit ourselves to just differentiability at a particular point. So as the definition says, if fx be a real valued function means the outcome or the output or the range, of course, will be all real values. Real valued function and a be any real number, then we define the right-hand derivative by limiting value as h tends to 0. I've just written in brief, f of a plus h minus f of a, where a is that point, that real number, divided by h, where h, as we know, is a very small interval. If it exists, then it is, of course, the definition goes, if it exists, then it is said to be right-hand derivative. Okay, I did not write on that part. This is how we denote right-hand derivative, r f dash of a, alright, and the left-hand derivative, limiting value of f of a minus h by same, f of a minus, divided by minus h. Where did that minus disappear? Divided by minus h. Divided by minus h, and denoted by L, left hand of f dash of a. Alright, so this is known as a right-hand derivative, left-hand derivative. This also, if it exists, if we complete the sentence, if it exists, is said to be, or is called the left-hand derivative of f of x at x equal to a. Here, of course, we are talking for the point x equal to a. By now, of course, you already know, because we have already considered a, no? So that's why this is at x equal to a, at a point. Alright, fine. Finished, you can pause there. Alright. So that's not differentiability at the point, that's just the right-hand derivative and the left-hand derivative. We are going to need that, that's why I have given it to you. So now let's write down differentiability. Differentiability. Alright, let's write down a function f of x. A function f of x is, see, definitions are very important, as I always say, we will always start with the definitions. After that, okay, the concepts in our own ways, in our own style. A function f of x is, I'm writing again, is said to be differentiable, is said to be is differentiable, said to be differentiable at a point x equal to a, remember, real number. Okay, if that's why I gave you that. If the right-hand derivative is equal to the left-hand derivative, if the right-hand derivative is equal to the left-hand derivative. Just like continuity, if the right hand derivative, if the right hand limit is equal to the left hand limit is equal to the value of the function at that given point, then we say that the function is continuous, isn't it? So here right hand derivative is equal to, if it is equal to the left hand derivative, right? Something more, the common value, if it exists, no? The common value, right on, the common value of the right hand derivative and the left hand derivative. Definitely if they are equal, then definitely they will be having a common value, isn't it? The common value of the right hand derivative and the left hand derivative is denoted by f dash of a. That's the meaning of derivative, and is known as the derivative, derivative, and is known as the derivative of the function f of x at x equal to a, where a is any arbitrary real number. Alright? So this is what we mean by differentiability at a given point. A function is said to be differentiable at a given point x equal to a if the right hand derivative is equal to the left hand derivative. How do we calculate this? I've already given you just previously. And the common value of the right hand derivative and the left hand derivative is denoted by f dash of a, which is also known as the derivative of the function at x equal to a if it exists. Okay? So when will it be not differentiable? It will not be differentiable. Yes, I'm asking you a very tough question. It is not going to be differentiable if the right hand limit is not equal to the left hand derivative. Sorry, of course the right hand limit will get stuck to my tongue for some days, you know that. Alright, so if they are not equal, then yes, it is not differentiable at the given point x equal to a. And as we all know, h represents a very small value and a positive value, very small interval. Alright, okay, that's it. So let's try some questions, that is like example. Of course, don't worry, I'll be giving you the textbook question also, but just to get used to it, an example, because there are very less questions. Right now, show that f of x, a practice question, x square is differentiable at x equal to 1 and find f dash of 1. So if it is differentiable, then it is derivable at the point x equal to 1. So this is one practice question. Alright, okay. Sir, you forgot something? Yes, I forgot something. Did I? Yeah, I forgot something. Yes, the concept, the geometrical way, the geometrical concept. See, continuity, as I said, in brief, okay, in very brief. I don't want to be confusing you, too many curves and all. So in just very brief, differentiability at a point. What do we mean by differentiability at a point? Differentiability at a point. What was continuity at a point? Continuity at a point meant that or in general, what do we mean by continuous functions? Continuous functions are those functions or curves, are those curves where we can just draw the curves without lifting our pen. That means, because if we lift our pen, there will be a gap. So where there are no gaps, then those curves are known as continuous functions. The curves of those functions are known as continuous functions. Continuous curves or continuous functions. And if you have to check at the point A, then what did we do? Then the concept was the left hand limit should be equal to the right hand limit, should be equal to the value of the function at that point. If all the dimensions, if all the values converge to one particular point, then there is no break, then definitely that the curve is continuous. That's what was the concept of continuity, continuous curves, no breaks, right? Differentiability. What do you mean by differentiability at a given point? Very simple. Listen, in very brief. Differentiability at the point simply means, for example, let's say you have a curve like this where x and y. So as you can see that as x increases, y also increases. You remember the concept of instantaneous, instantaneous, Taneous. It's similar to instantaneous concept, instantaneous acceleration, instantaneous velocity and all, but as I say, you can check out the concept of differentiation. I've already talked about that, so it's almost similar to that. Now differentiability at a point. Now look here, maybe at this point. So what do you mean by differentiability at a point? In very brief, okay, in very short sentence, I'm telling you, differentiability, when you talk of differentiability at a point, it simply means, the question is, can you draw a tangent to the curve at that point? Once again, can you draw a tangent to the curve, on the curve, at that point? If yes, it is differentiable. If no, it is not differentiable. That's why all the functions are not derivable. All the functions are not differentiable. Geometrical meaning is that, okay, all the functions are not differentiable. When are they not differentiable? When you cannot draw a tangent at that particular point of that curve, of that particular function. That means here, at this point, I can easily draw a tangent, isn't it? All of us, we know what we mean by tangent. So slope of the tangents, the concepts and all. But in brief, let's not talk about so many things. Tangent. So at this point, see, I would easily draw a tangent. That means this function f of x is differentiable at x equal to a. But the same function, its differentiability, I really can't say at all the points. For example, here, is it possible for me to draw a tangent at this point? If it's a straight line, then it's like not possible. It's almost like it's not possible at this particular point. So at this point, what happens? The function is not differentiable. What about here? Yeah, it is possible because somehow I can manage to draw a tangent. But what about again if it goes vertical? Then what happens? If it goes vertical, then what happens? Again here also, will the tangent exist? Because if the line is going like this, okay. I hope you're getting the concept. Now, suppose if the curve is like this, for example. Then in that case, is it possible for me to draw a tangent at this point? Not possible. Because tangent to it has to touch only one point, so it's not possible. I cannot draw a tangent like this, isn't it? So it's not possible. That means the function is not differentiable at this point. Here, maybe. Here I think, yeah, it's possible. See, so at this point, somehow I managed to draw a tangent. So at this point, the function is differentiable. But at this point, the function is not differentiable because at this point, I cannot draw tangents at that particular point. So that's the simple. Of course, if we just go on talking about the whole concept, we can just go on for the whole night. We can just go on talking because they are very vast topics. But in brief, I hope you have understood. Differentiability at a given point simply means that at that particular point on the curve, I will be able to draw a tangent. Then that function will be differentiable at that particular point. Okay? Alright, got it now? So I can draw a tangent. You just keep that in mind. Alright, for now. Okay? Got it now? I think that's fine. Alright, let's proceed. Got it? So I can draw a tangent at that particular point. So that means, okay, the function is differentiable at that particular point. You can draw tangents. Got it? So now, example. Show that the given function is differentiable at x equal to 1, and I don't want to waste too much time on this topic, and also that's why. Alright, otherwise, these are very huge topics. You can also check out the introduction on differentiation. There we have talked about slopes, what do we mean by differentiability, what do you mean by differentiation, all those. But for this particular topic, differentiability at a particular point simply means I can draw a tangent at that particular point. Ho gaya yaar, sir, kitna bar bolega? Okay, let's go to the exercise. Show that the function f of x is differentiable at x equal to 1. That means at x equal to 1. That's our point A. Let's find out the right-hand derivative, rf dash of A. What was that is limiting value as h tends to 0, f of A plus h minus f of A divided by h. What was our function? F of x equal to x squared. So what is our point A? Our point A is 1. So now let's use the function, substitute the function, that is limit as h tends to 0. That's going to be 1 plus h whole square, because it's x square minus 1 square divided by h. So that will be limiting value as h tends to 0, 1 plus 2h plus h square minus 1 divided by h. 1 we can just cancel. So that will be limiting value as h tends to 0. I can just take h common, 2 plus h divided by h, h. So now I can just use the value of h, 2e plus 0. What do we get? 2. So that's the right hand derivative. Let's go for the left hand derivative. Left hand derivative, that is equal to limiting value as h tends to 0, f of 1 minus h, because our point A is 1 here, no? F of A, that is again 1, divided by minus h. So that is limiting value. It's very simple. Once you have already done continuity, then it's almost the same concept, just the derivatives, the way we proceed, the procedure is slightly different. So 1 minus 2h plus h square minus 1 divided by minus h minus cancels. So then we'll be left with limit of h tends to 0. I can take minus h common, so it's plus 2 minus h divided by minus h. So minus cancels. So again I can use the value of h as 0. That is again what? 2. So the right hand limit, left hand limit, we get the same value. That is the right hand limit at x equal to 1, a equal to 1, and the left hand limit at a equal to 1. They are all equal. So now we can conclude, thus f of x is differentiable at x equal to 1, and the common value is f dash of a. That is how much? What is our a? 1, no? So f dash of 1 is 2. Got it? So that's what we have with differentiability, nothing much. That's why I think you have only 1 or 2 problems. Alright, so for concepts you can Google, or you can just check for yourself also. Alright then, let's go to the exercise. That's exercise 5.2. The other questions are from chain rule. That's about differentiation, and also that we will do later on. I mean after our concepts are finished. But yes, before that again. So that's how we do differentiability. Before that, you can just write down what is the relationship between differentiability and continuity. So there is a theorem which will help us develop that relationship between differentiability and continuity. So let's learn that. We are not going to be going for the proof, at least not for the board exams and all. So we'll be just learning the theorem. That might help us in the future in some other problems. Of course, in the textbook we don't have any problems based on that. So you can just write down but definitely for JEE and all the other exam preparations and all, definitely you're going to need that. Every differentiable, every differentiable function is continuous. Alright, every differentiable function is continuous, but every continuous function need not be differentiable. Got it? Every differentiable function is continuous, but every continuous function need not be differentiable. As I said, no, see this graph which I gave you, this is also what? A continuous function, but this continuous function is not differentiable at certain points. So it need not be differentiable, but every differentiable function definitely will be continuous. Okay, so that's the theorem. You just need to know that for your knowledge. Bus. Alright then, let's go to the exercise. The few questions in the beginning of the exercise are from differentiation about chain rule that we'll be doing in another video. Now let's just move on to the questions that are based on differentiability. So we have just two questions. Question number 9. So I'll just write on that question for you also. So some of you may not have the textbook with you now. Prove that the function f given by f of x is equal to mod of x minus 1. Mod of x minus 1 such that of course x belongs to the set of real numbers is not differentiable at x equal to 1. So you're supposed to prove that this is not differentiable at x equal to 1. Alright, so let's go for the right hand derivative f dash of 1 at x equal to 1, isn't it? So limiting value as h tends to 0, f of 1 plus h right hand minus f of 1 divided by h. So that is limiting value as h tends to 0. What is the function here? Mod of x, that is this, minus 1 minus f of 1 minus 1 divided by h. So that is limiting value as h tends to 0, mod of 1 plus h minus 1, this is 0 divided by h. So 1 cancels. So what do we have? Limiting value as h tends to 0, mod of h divided by h. Of course, that is limiting value as h tends to 0, h upon h. I'm just writing it for you. So this is of course how much? H by h1. So okay, let me just write it on the you might just think h tends to 0, 1. So it's not going to affect the value, that is 1. Okay? You can write it down. Alright, let's go for the left hand limit. So you can start with the left hand limit. Alright, me, that lazy person, I'm just going to rewrite over this. Left hand limit is equal to, so that's going to be 1 minus h divided by minus h. So this is going to be 1 minus h divided by minus h. Rest of the things are all going to be same. So this is 1 minus h minus h. So this of course will be now minus of mod h upon minus h, minus of mod h upon minus h. So that would be minus of mod h, of course it will be plus h, but this will be minus, because this we cannot change, minus h. So this will be minus 1. So the value will be what? Minus 1. So as you can clearly see that the right hand derivative at x equal to 1 is not equal to the left hand derivative at x equal to 1. So f of x is not differentiable at x equal to 1. It's not differentiable at x equal to 1. Alright, so you can pause the video there to write down. Okay, chalo. So that's what it is, differentiability. So it's not a completely new topic. I mean, we have already done continuity, you know, so most of the things are almost same the way we solve. Question number 10. Prove that the greatest integer, we have already done problems on greatest integer function in continuity, so it's not going to be completely new for you. Defined by f of x is equal to, of course, greatest integer function, which is also known as the floor function, if you remember, no? I hope you're watching all the videos. Is differentiable, is not differentiable at x equal to 1 and x equal to 2. So I'll not be talking much about greatest integer function here. Okay, we have already done problems on greatest integer functions before. So I hope you're following the videos. So we're going to go straight to the solution. So let's start at x equal to 1. So let's start with the left hand derivative. So limiting value as h tends to 0, f of 1 minus h minus f of 1 divided by minus h. So that is going to be limit as h tends to 0, greatest value of minus 1 minus h divided by greatest function of 1 divided by minus h. This is going to be limiting value as h tends to 0. 1 minus h, what will it be? 1 minus h. What will be the greatest integer function of 1 minus h? 1 minus h, that is slightly less than 0. Let's say 0.9. So what is the greatest integer value of 0.9? Of course it's 0. That's why it's called the floor function. We write on the smaller function now because fine, I see again I'm discussing 0.1 lies between 0 and 1. Which is the smallest? 0. That's why it's called the greatest integer function, because it's the smallest. Nearest one and the smallest one we write. We talked about these functions. So this is going to be 0 minus 1 divided by minus h. That will be limiting value as h tends to 0, 1 by h. Now 1 by h of course will be infinity or not defined. So this is not defined for us. So the left hand limit is not defined for us, or infinity. Okay. So done. So I'm going to rewrite the right hand limit over here, as you know. Sir, you are also very lazy. I know I don't want to rub and write, so that's why. So right hand limit 1 plus h, this is plus. So 1 plus h, this is plus. So 1 plus h, what will be? That's like 1.1. So what is the greatest integer value of 1.1? 1 minus 1 divided by h, because this value is going to be 1. H is a very small interval, so it's going to be 1.01001. So of course we will be writing 1. So this is of course what? 1 minus 1 is 0. 0 by h is of course 0. So this is of course how much? 0, 0, 0. So as we can see that the right hand derivative is not equal to the left hand derivative. So we can write down the conclusion. Hence, please write down, hence, f of x, the function, is not differentiable at x equal to 1. Okay? Alright, now at x equal to 2, let's go for the right hand derivative. Right hand derivative. Limit h tends to 0, f of 2 plus h minus f of 2 divided by plus h. Okay, that's right. So that's limit value as h tends to 0, 2 plus h minus 2 divided by h. So that is limiting value as h tends to 0, 2 plus h, 2 minus 2 divided by h. Again, this is 0, because 2 plus h means 2.01. So the greatest integer of 2 is also what? 2. Left hand derivative, limit value as h tends to 0, f of 2 minus h minus f of 2 divided by minus h. That's going to be limiting value as h tends to 0, 2 minus h, greatest integer function, f of, this is also 2, this is minus h. So 2 minus h, that's again like let's say 2.01, so minus h, sorry, 2 minus h, slightly less than, so let's say 1.99. So what is the greatest integer function? Because 1.99 lies between 1 and 2, so that we will be writing down the smallest one, isn't it? So that's going to be limit value as h tends to 0, minus 1 minus 2 divided by minus h. Write down minus 1 minus 2 divided by h. Not minus 1, sorry, plus 1. What am I doing, man? Plus 1. 1. 1 minus 2 divided by minus h. So here also almost the same, so that's going to be limit value as h tends to 0 minus 1 by minus h, that is again limiting value as h tends to 0 1 by h, that is of course again infinity, not defined. It's not defined because 1 by 0 we know it is not defined, so we can just write infinity also, no problem. For here calculus and all we use that, no problem with that. So the conclusion, the right hand derivative at 2 is not equal to the left hand derivative at 2, because left hand derivative gives us something that is not defined, or we can just write infinity also, no problem with that for calculus and all maths, no, not a big problem, calculus. We used to write infinity also. So f of x is not differentiable at x equal to 2. So knocked out differentiability also. Okay, so that's basically what we have with differentiability. It's a very small topic, so please do not miss out any marks from this particular topic if it comes in the exams. Okay, it's a very small topic, so just 1 or 2 odd questions from the textbook. I've given you an example also. So, and if you really want to know more, of course you can just, of course there will be new videos provided also, so you can just check out, or you can just try to, try to learn on your own. That's the most important thing. Okay, all right then, so that's it. I'll see you with differentiation chain rule. All right, thank you all for joining. I hope you've liked the video. Please give me a like, share, subscribe. Bye bye, stay safe.